Thank you very much. Thank you very much, first of all, for the organizers, in particular the Dutch Embassy, for inviting me here in this very prestigious place where you feel history. Now, I'm coming from Radboud University, which is in the city of Nijmegen in the Netherlands, which is the oldest city of the Netherlands that we know, goes back to the Roman Empire. So we know a little bit about history. So that, I hope I feel a bit comfortable today here as well. But what is here so different is that you feel the big history of science. You immediately feel what UK brought to science. And if I think about this Faraday Museum here, I immediately think about the high magnetic field lab that we have in Nijmegen, which can produce the strongest static magnetic fields. And making that super big magnet, of course, would not have been possible without this pioneering work of Faraday. And then I think about my experimental colleagues, which discovered experimentally ultra-fast inverse Faraday effects. So I immediately see lots of connections. And then I realize there is also lots of expertise on neuromorphic computing, which is the topic of today, which is spearheaded, which is led, which is stimulated here in the UK, and this will also come back here. So that's why I feel so honored that I can present some of the things which we are super excited about, which adds to this neuromorphic computing. So let's start with why. Why is neuromorphic computing such an interesting, and why should we think about it? I tried to come up with something that may be close to you. So this is what is the BBC publishing on their websites, and which came into the news. That nowadays, we're not talking about energy efficiency anymore. If we talk about computing, we talk about energy. We just don't have the energy of normal, like power plants, to cope with the energy cost that today's artificial intelligence needs. So we have come to a situation where everybody uses artificial intelligence, but we need, like infamous, because this nuclear power plant once broke down somehow, and now it's kind of being reused and being bought essentially by Microsoft to use the energy for their big AI models. So that's a big kind of threat. Like, it costs a lot of energy, but also the climate effects of that are, of course, huge. So that's one reason. And then a next reason is privacy, and security. So we're now in a time where we just kind of has no substitute in history, where we just share things which were kind of close to us, not even the pictures, because pictures are really recent, but even kind of health things. We just share them with everybody, and with everybody means it goes from us through our mobile devices to big data centers. And that kind of privacy information is kind of transferred, hopefully, in a secure way. And then the other why is, where is this data being transferred to? So we are kind of here at the right, like the smallest country here in Europe, or not really the smallest, but Netherlands, and then UK. But we are sending this to data centers from companies which are so large, and only they can afford, and they are hungry for our data, because they like it so much, but we don't have control on that. So this is limiting sovereignty. Now, these were all the things I wanted to say about negative things. I'm an optimistic person. Because, okay, sorry, I want to highlight here that people here from London made a very pioneering paper which showed that the pace at which this is developing is just completely unsustainable. Even the big tech will not be able to scale this much further, because the total power that we want to use, like the power hungriness of computing, is increasing, not with kind of Moore's law, which was kind of up to 2010, but now it's doubling every 3 to 4 months. We just don't have technology that we can improve with the same rate. So of course, standard computers become a little bit more efficient, but the amount of computing that we want to do is just increasing so much more rapidly that there is no sustainable future of this model. So now comes the positive thing. So I see many new kind of opportunities. Like suppose you have a computing paradigm which is very fast, extremely fast, and at the same time very efficient, like in terms of algorithm, but also very energy efficient. Then you can do much of the computing just at the place where you produce it. So like at the edge, this is how we call that. Like, for example, at your mobile, you don't have to send the data away. And that means that you can also limit a lot sending this privacy-sensitive data. So you can somehow deal with data, which we like, which brings new services, but without all these security problems. And because it's new, and this take back, I took it because I thought this was kind of a well-known term in the UK, take back control in IT. Because it's new, we're not relying on the already big people, the already big tech, but we can hope that we can also get something of that back here. And what is the topic today, which makes me as scientist so excited, is that we have the chance, and this is what I will try to illustrate to you, this potential to compute things which are just not computable with the digital technology that we have today. So that means we could break computational barriers. Okay, so that's the promise, that's the enthusiasm, that's the inspiration that I have there. And then I have to explain to you in a simple way what I mean with neuromorphic computing. So neuromorphic means kind of similar to the morphology of the human brain, so brain-inspired. And what is so different in brain-inspired computing than in standard digital computing? Well, if you take a step back, actually the digital computers are kind of advanced variants of the abacus or of the Pascal computers, which are completely mechanical devices to do repeated calculations, which for humans is somehow a bit complicated because they're kind of sleepy or whatever. So then they make errors. And digital computers don't want that. And the design, actually, that's one of the famous names that I didn't mention yet. Of course, this was due to Turing and John von Neumann. They designed a computer which is universal, which can do everything. And to do that, they have a separation between the places in which you do processing. So these are these red squares here in this picture, and the places in which you do storage. So you have storage of information, of data, say just bits, zeros and ones. And they need to be transferred to the processing system to do a processing task, and then the results should be transferred back. And on top of that, you also have to transfer that program all the time to this processing part. The instructions should be there. And this separation of processing and storage leads to a lot of data transfer, which results in this 50 megawatt number, like for the best supercomputers that we have today. And that is inherently due to the fact that this is a serial type of operation, completely digital. We made it so like deterministic as possible by using this digital hardware. And still this hardware is there, and still the human brain, which is a completely different architecture, can do certain things still better than these super advanced supercomputers. And that is because the brain architecture is like local. It's not this non-local separation, but in the brain, you see this on the top right, you see that processing, these red neurons, that those are the processors of the human brain, are connected to the storage very locally. So there's lots of local data, lots of memory available directly at the place in which you compute. So that means that processing and storage is integrated, and therefore you can do parallel computations. And the interesting thing is that this is completely analog and also very noisy, so very different from this digital paradigm. So if we somehow can find out how to deal with these kinds of principles in devices, in computing devices that we design, say non-biological brain-inspired computers, then we might hope that we can kind of gain similar efficiency gains and do computations which we cannot do now. Okay, I'm going to tell you a lot of things, but I also would like to have it a little bit interactive. So I'm now trying to ask a simple question. Could we have predicted this nuclear power plant? So, and in fact, the answer is yes. This is a slide that I borrowed from Intel. so not borrowed, it's just you can find it on the internet, which says power density, which is the vertical axis in watts per square centimeter. That essentially means power of a chip, because a typical chip is 1 square centimeter. And the horizontal axis is feature size. And feature size is kind of equivalent to year, because this is Moore's law. Feature size is kind of the smallest part, the smallest line that you can make, the smallest part of your chip. And at the time that I was say, stimulating or motivating or convincing my parents that they should buy a computer, that was the 86th time. So this is on the bottom left there. So that was the first computer, and that was, okay, 1 watt per square centimeter. Okay, that's 1 watt, that's maybe fine. But then soon these Pentiums came, and then it already became 10 watts per square centimeter, which is the equivalent of the power density of a hot plate. So of course, a processor is smaller than a hot plate, but with the same power density, you can just cook. But nobody was so happy. There were errors in this Pentium machine, so they went on with Pentium 2, Pentium 3, and the next order of magnitude is 100 watt per square centimeter. So that is the power density, which is equivalent to the power density of a nuclear reactor. So that's already a nuclear reactor. You can also go a bit further, by the way. So if you go 1 order of magnitude more, you have a rocket nozzle. And if you're then not happy enough, you can fly to the sun, and the surface of the sun, that's 10,000 watt per square centimeter. Okay, you will not reach this alive, but okay, that's a... And you can ask yourself, where is actually technology today? That's 2 nanometer, right? So wonder if it's really the chip is moving that fast. But this is what is now helping us, because now I want to make a little poll. So I thought we can do it digital, but because this is such a historic place, I felt maybe it's better to do it just with hands up, A, B, C, so A, B. But the question is, how many smartphones can be supplied, so the power, we need to supply the power of that chip on the smartphone with 1 rod, with the energy of 1 rod of nuclear fuel. So who thinks A, 100 smartphones? Oh, that's not much. Oh, no, 1. Oh, okay, a couple, yeah. B, 1,000. And C, 10,000. That's the majority. Okay, I'm going to show you a very simple back-of-the-envelope calculation, and which is, what is power density? We just saw that power density of the nuclear reactor is kind of the power density of today's chips. That's 100 watt per square centimeter. Indeed, typical GPUs also are in that ballpark. Then area. Okay, a nuclear rod is 10 centimeter in diameter. Smartphone chip is 1 square centimeter. If you divide them, it's just 75. Yeah? So next time you take your smartphone from your pocket, think about this nuclear reactor. Actually, it's not just Microsoft who has it, but also you have it. Okay, so that is kind of why these digital computing paradigms are not good enough. And now I would like to talk about the paradigms, not paradigms, but the computational challenges that we are excited about, the things that we want to compute but cannot compute today because of just limitations on the hardware. And then later I will also talk about 2 specific types of neuromorphic algorithms. I call them neuromorphic because they have this separation between processing and memory. There are also other people which say, no, only spiking hardware is neuromorphic. I have a little bit of a broader definition. And then I will end after 1 hour. I hope I make that in 1 hour, or I make it with you, with future prospects. So what are computational science challenges? So the grand challenges that we have, for example, are in material science, or even in like high energy physics, in fundamental particle physics. We have many quantum particles, or even if we are already happy with classical particles, if we just think about the many particle problem of the universe with just many of these like Earth-like planets which are moving everywhere, if we want to solve that problem, we also have a many particle problem. And in the most extreme case, this thing scales. That's why I put this 2 to the power n. That's actually a simple estimation for only, say, binary spins. Spins are kind of the analog of magnetic moments in the quantum world. So exponentially with this number. So that's a huge parameter space, and we just cannot fit on classical computers. But if we can solve many problems, like we can understand better materials, we can understand fundamental properties of matter better. And that, of course, has huge ramifications in all kinds of application disciplines. But even if you're not interested in these applications, in science we have also fundamental, like big science infrastructures, which produce huge amount of data. And this is a picture of a detector that's used in CERN, which produces the astronomical number of more than 100 petabytes per year, which need to be processed. And you have to realize, these people in particle physics, they don't have a computer or a hard disk drive in which they can store this information. So they need to throw some bits away, and not a bit of bits. In fact, 1 in a million of these events that they want to store is relevant. So the other is just already known standard model physics. We know it. We don't have to store that data. We only want this beyond standard model physics. So they need super fast and super efficient like data analysis equipment. So that's this, what we call high throughput computing for analyzing their data. And that's not even the largest data producing field. You have astronomy. This is a thing. This is a picture from LOFAR, what was the name? The LOFAR telescope is a low frequency array, and this thing produces over 300 petabytes per year. And now they are building SCA, the square kilometer array, which is even producing data for which they cannot afford even just commodity hardware to analyze the data. So they need something else. And then there are also very humble people that try to understand the climate. And if you want to simulate that on a classical computer, okay, that also is even beyond an exabyte per year. And the problem is that, okay, this is what is kind of happening. We have increase of computing power, but yeah, okay, we can maybe go from 30 to 50, and some very rich countries can maybe buy a supercomputer of 100 megawatt. But that's also only a small portion of the scientists that can use that. So if we want to solve these problems, we need something else. And this is where neuromorphic computing can help us. Or this is what I try to get you inspired by, that neuromorphic can do that. And what I will do now is focus on this many-body problem, because that's the problem which is closest to my heart, which actually all these grants that people award to me are given for this understanding these properties of many-body spin systems. And what is the physical problem that we would like to understand there? So we know very much how technology today works. So if you think about magnetism, so this is about ultra-fast nanomagnetism, but let's first start with magnetism. Then we deal with magnetic bits. Magnetism, these are tiny magnets. They can point up, say North Pole up, that's this 1. And if you do North Pole down, that's a 0. And those kind of information is stored on hard disk drive. This we understand very well. It's super nano. It's 1 nanosecond writing time, or not 1, but order nanosecond. It's order nanometer like dimension of this bit. And it's also less than a nanocent. That's why everybody uses it. So it's kind of super nanotechnology. But yeah, as scientists, we are never happy. We would like to scale this further down. And we only know physics again very well if we are in this super bottom left corner, where it's just a single particle, so that we can solve analytically in some cases. But in fact, we have many experiments in this strange regime of below nanoseconds, like picoseconds, order nanometers, which are super counterintuitive. We cannot use the classical theories that we are used to understand what is happening there. And we would like to simulate that, but then we have to solve this many-body problem. And the trick is that we have to kind of bridge this classical and this quantum world. So it's not just that we want to have a quantum computer that can solve this. No, we want to have a method that can interpolate between the quantum problem and the classical problem. And that's what we look after. And one of the fascinating discoveries of the past years was the development of a special type of neural networks. So neural networks are in principle algorithms which run on classical computers, like this is this kind of AI inspired. And people realized, very smart people, Giuseppe Caleo and Matthias Troyer, that you can represent quantum problems actually classically with a neural network. So how does it work? Okay, this is maybe a bit technical, but what you see here on this slide are all possible quantum states. So those are all states kind of up, down, up, down, and then the other black bar is down, down, up. And so you have many, many different states, exponentially many. So of course we cannot store all these systems, but what you can think with neural networks is, okay, this wave function that describes this system, which in principle, if we know that wave function, we know everything we can know of the system, okay, that is still just a function. And a function we can approximate with a neural network. We have universal function approximation theorem for people that like these kind of mathematical statements. And that means that we can now think of solving these problems in not exponential time, but in polynomial time. So the scaling is much better, and that means we can simulate much larger systems. And the excitement came actually, and well, that's also, again, a UK angle on this, because the model that they introduced was the restricted Boltzmann machine, and the restricted Boltzmann machine was developed by Geoffrey Hinton, and Hinton is just this year awarded for the Nobel Prize. And the interesting thing is that in the reason why is this Nobel Prize for AI attributed to physics, so it's a physics Nobel Prize, they cited this paper of Caleo and Troia because the use of AI in physics, and this is a key example of that, and already this network was able to outperform the best, say, what we call variational methods that were available at that time. And here's one parameter that you will see more often later, so be reminded. So you see a neural network, these red spins, these red like little balls with arrows through it, those are the variables of our system, and that we call input, so the visible units, and the blue ones, those are the hidden units, and the ratio of them is we parameterize with alpha, which tells to us how complex this network is. So the larger this alpha, in principle, the more complex problems you can simulate. So we jumped on that because of the potential for 2D systems. There were many methods that could be done for 1D systems, but there are not so many real magnets which are 1D, and I was interested in magnetism and very small magnets, so I wanted to have 2D magnets, and this method seemed to be very interesting for that. And then we did some simulation, and this simulation is inspired, I alluded to a little bit in the introduction, like my colleagues use ultra-short laser pulses. So this is just a mathematical description that explains to you how a laser pulse interacts with a magnet. But the finding was that we discovered something like supermagnonic propagation. So what is supermagnonic? So supersonic you may know, like this is the jet fighter, which goes through the sound barrier, and you hear this big sound crack. And here we found something similar, but then in a magnetic system. So also in a magnetic system, just like in air, you have waves, or just like with light, you have waves. And normally you think in any system, nothing can be faster than the speed of light. So we also thought that would be the case in a magnetic system. But in fact, what we found, and that you see here on the right, is that if you capture the velocity of the dynamics of this system, the velocity is higher than the highest wave velocity that we have in this magnetic system. That's why we called it supermagnonic. And this thing shows that, in fact, this is kind of interpolates between this quantum regime, in which that velocity is higher, and the classical regime, which you see at long time scales, so that's the top right of this figure. There we recover classical physics, and on short length scales we have this quantum physics. So this is an interesting method now. We can simulate this crossover, at least for one case. So then we wanted to go on, because this is now prediction. Can we somehow verify that experimentally? Is that possible? And in fact, we already did a lot of experiments together with, we did a lot of simulations together with experimentalists, which found evidence for very heavily fluctuating small magnetic domains. So I told you about magnetism, so you can visualize all spins are up. That's kind of simple ferromagnet, but you can also have a situation in which in a certain region they point down, then you have a small domain wall in between these two systems. And here we see very rapid fluctuations of them. And these are classical fluctuations. And the key insights were from a system, a classical simulation, on 100 by 100 letters. So that is nice. But yeah, okay, so what we would like, we know that the microscopic world is quantum. So we would like to simulate these kind of things fully quantum mechanically, being able to capture both this classical and quantum limit. And then we did a simple calculation, and we already see, okay, this works. We can do this 24 by 24. That's kind of the largest that we can do. It takes us already 6 hours for one optimization step. but one optimization step for this large letters is just 75 days. So there's no way that we can do this. So that is why the problem that we want to attach. So here we kind of have a killer application, something that we cannot compute today. If we calculate it, then we can have access to new physics, but we cannot do it. And why can we not do it? So this is now a bit technical, but the short answer is, okay, there are two types of calculations that we do have to do a lot. Many times we have to calculate an input state which gives us some output. So that's in machine learning we call this an inference step. And that inference step is basically a multiplication of a vector, all these input states, with a matrix. And another step which takes a lot of time and which is taking us most of time for all our calculations if the system is large is the sampling. Because these number of states that are there are still so many, we cannot take them all. We have to just find the most probable ones. And the method that you do for that is Monte Carlo sampling. So now I started with my own fascination, and you may like it or not, this ultrafast nanomagnetism, but we ended up with two very common computing primitives that everybody, even just in ordinary AI, use a lot. So if we can accelerate these two, then we might have the key to unlock this breaking of computational barriers. And the first example that I do, so for this inference, we are looking to in-memory computing to accelerate that, and for this sampling, we look at hardware which is inherently stochastic and therefore might be able to have much better performance. Okay, so then let's go to this first example of neuromorphic computing. This is this in-memory computing. And let me remind you, why is this in-memory computing logical? So this is a model of abstracted mathematical model of artificial neural network. And there you have lots of these local synapses, which is the memory, and lots of these local processors, these artificial neurons. And at each of these neurons, you calculate the function, which is just some complex, sorry, not complex, just some nonlinear function, acting on the multiplication of an input vector times a matrix, this weight matrix, which is indicated here as W. So that we just have to do a lot. So if we accelerate that, we accelerate this whole calculation. And a physical way to do that is this in-memory computing paradigm. And in principle, this is nothing else, in the simplest description, as a matrix directly implemented in hardware. So here you see 3 rows and 3 columns. So just as a matrix has rows and columns. And at these connection points, you have small memory elements which have adaptable resistance. So how does that work? So let me try to go through this slowly to bring us to the key point of why this can have an advantage. So you can just understand this. I don't know if there are people that are from electrical engineering there, but this is just circuit laws. If you focus on a single resistance, you have Ohm's law, which says that the current that goes through this resistance is just the voltage that you apply to it divided by the resistance. Or you can also say the voltage times the conductance. And that you have, of course, for every resistance. And then you have the circuit law, Kirchhoff's law, that says, okay, there is no sink or so of current, so the total current must be the sum of all these 3 currents. So that means you can put your input voltages on, and then you get on the column, at say this I1, you get your outputs, just by physical motion, in this case, physical currents. And because all these resistances are fixed, so you have stationary weights, you get rid of all this transport of weights, which is normally in an ordinary computer. So that's why you break this barrier of this continuous transport. So that's already something efficient. And there are many materials nowadays that we know that can realize variable resistances, which also keep their memory. So these are what we call memristors, resistors which have memory. You can make them from phase change material, metal oxides. MTJ stands for magnetic tunnel junction, of course, coming from magnetism. I like them a lot. And also ferroelectric tunnel junctions. They're tunable and they are non-volatile. And then you come to the point, and this is not something that I discovered. These engineers know this already for long. If you now not write this anymore in terms of voltages and resistances, but just as a matrix vector multiplication, what you see is you come with your input vector and you get your output vector. And you have normally, if you have an input factor of n elements on a traditional digital computer, you have to do all these multiplications one by one, so serial. So that means that the calculation would be order, this is how this O with n squared there, how we describe this, it's order n squared. So it scales with n squared. But now in this in-memory thing, we just can apply these pulses, and we get the output pulses just in one step. So in digital computing, this would mean like, okay, just one clock cycle of your computer, and you do the whole calculation. So this is order 1. So you essentially get a scaling factor n squared. And that's the key reason of why this is expected to have a big advantage. So, okay, it may be that it's not so large. So this is just a simple 3 by 3 matrix. Maybe, okay, that you can even do just, every human can do it. But and then it can be that, okay, maybe that computer is not so fast for this very small thing. But if you make n just very large, at some point the scaling factor should pay off. And that's what we try to find. And this is a graph to show that indeed, also this is what the engineers calculated, the effective binary operations per second, and that is a number in the tera range, so this TOPS, tera operations. So that's really a huge number, and you see that as time progresses, these crossbars, they move up and up and up. And what you also see, that somehow these crossbars are made of relatively large resistances because the power is now in the milliwatt range. Compare again to this 100 watt that I already shown before in the beginning of standard computers. That's immediately a factor 1,000 that you gain. But we have to be fair here. This is just the memory of only the crossbar itself. In reality, you have, of course, some peripheral equipment. But I will come to that. And then, okay, so the type of research that we then try to do is to say, now, let's take just a practical user point of view. We are computational scientists. We want to do the calculation. So we do it for the networks that we have. And let's see if there is some advantage. And this is what we did for the condensed matter use case. These are these neural network quantum states, just in a little bit of a different representation. And we did it also for a similar neural network calculations. This was by my colleague, Sascha Caron from Radboud University, who developed a smart neural network approach to find these anomalies. So to find these 1 in a million anomalies of the standard model. So those two models we have, so let's see. So how can we do that? Okay, so then we of course have to do in some way benchmarking. And we developed a simple algorithm. So this is my PhD student Dominique did that, using the software developed in Barcelona, which can really monitor how much energy is a single job on a digital computer taking. And we did that for CPUs, standard CPUs, and okay, this is a couple of years ago. Now you have even better GPUs. But this was the V100 GPU that we used. So this is just an algorithm which optimizes it a little bit such that we don't compare it to a completely stupid calculation that you say, okay, just by designing your algorithm, you have a very bad benchmark. This is what we avoided. And then we also, and this was a little bit of more effort, and here you see that it's not just having a crossbar. So here in this left, you see what the type of memory element that was used. This was work together with the very smart engineers at IBM. And only in the middle, there's a 512 by 512 crossbar. And then there's lots of peripherals like analog digital converters, digital analog converters, some local processing. So we really try to capture that all. And then the nice thing is that, okay, this in principle you can buy. It's based on a design, on a chip that they have, the Hermes core. But of course, you cannot make for every new scientist that comes a new chip, because these chips also are a couple of million worth, so that's kind of a lot of money. So we cannot just try that. But the engineers, they know all the components, they know all their properties, so we can very accurately estimate the performance in terms of energy and latency of these type of designs. So then, okay, we did the test. So this is the result for condensed matter. So the right one shows you how fast you can do the calculation. So you see the throughput at the vertical axis. The horizontal axis shows you this scaling parameter, this alpha that I introduced to you before. So the larger the network, the more complex more accurate you can get your solution. And then you see that actually the GPUs and the CPUs in this case are still a bit better, although as you increase the network, already they come down. And what you also see is that although the kind of performance is, in terms of runtime, is the same, you see in terms of energy it's already a factor 100 better. So I actually had to cut this vertical axis because if I would do it, all these lines of the GPUs would just be on top of each other. But then we were kind of lucky because this was a small network and this particle physics use case was a little bit larger. And then you see actually if you make the network larger, then also the storyline, the result changes because now this dashed line, this black dashed line is completely on top. So the highest throughput, and which is flat, just by the design, I announced that this is order n squared to order 1. It really works out if you do this, if you make this design, whereas the GPUs and CPUs, they become worse and worse the larger you have your model. And now you get even factors like 20 improvements on the throughput and up beyond 1,000 times more energy efficient. So that makes us very exciting, and we are also super excited that we kind of rediscovered that it really works in that way, that, okay, you go from this n squared, which is how it is, which is why digital hardware becomes worse and worse for large models, which you don't have here for the in-memory computing solution. So this really looks very promising, like, okay, this is just comparison runtime and energy, which is for practical users very important. Of course, we also have to assess here how accurate is this, how often can you use it before the device breaks, so endurance and all these kind of things. But this really demonstrates the potential and the scaling advantage that you have. So that's an example of accelerating just standard neural network inference. Now I promised you a second example. So let's not make it too fast, but the one thing I didn't do yet was stochasticity. I did analog, so this hardware was analog, it was parallel, but we didn't embrace anything of stochasticity. And now I would like to provoke you a little bit more. So the question is like, we talk all the time about the energy efficiency of the human brain, which is also efficient as compared to supercomputers, but how efficient is it actually? So can it be maybe 1,000 times more efficient? This is answer C, or 1,000,000 times more efficient, or I always have to be careful, 1 billion times more efficient. So let me see, who is for 1 billion? Ah, nice, nice. It will come back. Who is for 1 million? Oh, one more for 1 million. Nice, nice. A. Who is for B? Ah, but the majority seems C, right? Is that correct? Oh, no, you don't dare to be any majority. It is not democracy. Science is not democratic. It's just one answer. So I have to tell you a little bit about the basics of energy efficiency. So this is again from IBM back in the 60s. They already found out a physical limit. So if you do a calculation, typically you do it in an irreversible way. So that means that there's kind of, okay, you combine two numbers and you forget the past. If you forget something, that means that in the physical system there must be some kind of production of a concept that we call entropy. I teach this to first-year students. They are always very confused. But I think everybody knows that entropy always increases. Like, is this something that nobody knows? Well, yeah, okay. So, so that's indeed a concept which says kind of the most probable situation is the situation where most of the situations are tried. Like, it's the example of if you try to clean up your cupboard or so, it's very hard to keep it cleaned up because there's just only a few configurations of all the cups that you put in there, which are very nice. And there's just many more possibilities to put the cups in a kind of random and disordered way. So that's why it's hard to keep it ordered. And the point is that that energy production that should then come is order kT. So K is the Boltzmann constant, or Kb is often called. And that room temperature, that's just a minute amount of 10 minus 21. So that's the zeptojoule. I don't know if you ever used the word zepto, but it's the number that we have, the label that we have for that. Okay, let me do a little bit of basic thermodynamics. We have conservation of energy. We have second law, entropy, which in statistics means the probability, so very high probability, so many states are visited means high entropy, only one state visited is zero entropy, so it's kind of pure state if you like quantum physics. And these two are related by this heat production. Now let's do a simple calculation. So if you have a binary system with 0 and 1, so that's the kind of initial state. I don't know really what it is, but the final state should be definite 1. So initial state is kind of disordered, so that has the highest entropy, logarithm of 2, and the final state is just one possibility, so entropy 0. So the change of entropy is negative. So this looks like kind of impossible, but no, this is allowed because it's only the entropy of the system which we force from a random state to a very well-known state. So the entropy of everything, of course, cannot decrease. But from the system it can. And now we apply this to thermodynamics. We say, okay, states up and state down have the same energy. So the ideal situation is that all energy that you need for this is due to work that you apply. And then we can relate this in still a limiting case where the temperature is fixed. And then we find out that indeed, okay, the work that you need to do to make this simplest possible reset to 1, how we call it, operation, is this kBt log 2. And that's why we have Landauer limit. Actually, there's something interesting. There's a nice startup here in UK which actually also wants to avoid Landauer limit. So then it can be even lower. But let's not get too much diverted from that. This is already a very minute number. So suppose we have the brain working at this limit. What would we get? So the number of synapses in the brain is a huge number. So this is 100 trillion, 10 power 14. So it's really, really huge. Okay, 10 minus 21 joule. And now we have to estimate what is the typical clock frequency in the brain. This is kind of the spiking time. So on average, how often you see spikes. So that's about 10 hertz. Okay, maybe 1 hertz, 200 hertz, but let's take the median of that. And then the theoretical power that the brain could possibly operate is just 1 microwatt. So the people with 1 million, the B, that was not a small minority, were right. So in theory, you can make the brain even more efficient than it already is as compared to supercomputers. So I was teaching this a couple of years to the students in neuromorphic computing class and also in the first year class in theory of heat. I found this a kind of funny example. And then, but I never really talked with neuroscientists. But then I stumbled upon this paper. It was from real neuroscientists published in PNAS, like Proceedings of the National Academy of Science. So, and they say, if you look at the neurons, it can be even 100 million more efficient than the brain is doing. So all this is saying that still the brain also has a lot of transport of information, and the individual computing elements, they actually can be much more efficient. Okay, so it can be more efficient, and now I connect this to this stochastic type of computing, because a stochastic computer is not like a digital computer. So let's go back to spins, because I like them so much. Digital hard disk drive, they have spins up, they have spins down, and there's kind of a huge barrier, I don't draw it here, but between these two types of spins, so that the up can never go to down, because then you would kind of have a hard disk drive. With Alzheimer, nobody wants that. You want to keep the information, so therefore you make this huge barrier. But the probabilistic computer is kind of designed to forget. It just wants to hop up, back and forth, basically driven by thermal fluctuations. So you make the barrier very low, so essentially this one operates without any energy input that you need to give it. It's just random. And these random numbers you get for free, and in fact with magnetic systems you can make these random number generation very efficient. And so then if you have all such kind of random number generators, so just flipping bits, then you can make something which looks like what people call a stochastic icing machine. So now you have these red and blue balls are like, again, these visible and hidden units, which are just continuously fluctuating all the time. And we connect them. So we connect them essentially with this kind of crossbar, so it's like kind of all p bits are connected to another one. That means at a certain point in time, this individual p bit feels all the other p bits, whether they are up or down, and depending on that, they will change their probability of flipping. So they flip with a certain rate, but this probability is dictated by this force, this I, it's I, it's not a current actually. Well, you can also do this current, but it doesn't matter for the moment. So that's kind of this synaptic connections and these stochastic neurons. So now the whole probabilistic calculation is kind of just the energy cost of this crossbar and the flipping you get for free. And the funny thing is now, this is a theoretical result. This goes back to Gibbs, again, a famous British scientist. Sorry, I say Gibbs. No, wait, I'm going too fast. Gibbs was not in, he was in US. If you force these p-bits to behave like the sign of this tangent hyperbolic, anybody heard about hyperbolic functions? Or is it super abstract? Ah, good. Yeah. So, so it's kind of this nonlinear function that we also saw before. That's the stochastic neuron. If you enforce them like that, then they will minimize the probability distribution of that Hamiltonian that you have there. So this Hamiltonian is just the coupling of all these spins in the system, and it also has a simple, okay, let me call it Zeeman field. Zeeman was Dutch. So where now do we get the advantage from? So this icing machine, by design, all these bits, they flip just in parallel, say. You don't have to have a clock which says, I need to flip or what to do. They just do it, all simultaneously. Whereas if you think about the standard way we do sampling on digital computers, this is inherently serial. You have a given configuration, you propose, okay, maybe let me flip this one here. Okay, I flip it, and then if that energy is better, then I accept it, and if it's not better, then I may accept it with a certain probability, and in that way I create what people call a Markov chain, which is inherently serial, so that's why typically you need on the order of the number of p-bits that you have, and that's why this icing algorithm makes you something which is order the number of p-bits that you have to something which is order 1. So again, if n is large, this might have an advantage, and we would like to know where is this advantage. And that is really something sensible, and let me highlight here the work of Kerem Kamsari, who is really pushing a lot this probabilistic computing with p-bits, and we can really make it with magnetic devices or with like reconfigurable computing, like by smart hardware design, still based on CMOS. You can really make massively parallel, so really calculations at a scale of the order of millions. So now let's see, we don't have that computer right now, so let's see what we can analyze if there is any advantage. Now we calculate again the energy as a function of n, this number of steps that you need to take to go to convert to have the optimal solution, which might still be different, right? So if you look at this one, there kind of are the number of samples, you see it on the left, and which is ns, on the right we call this ms. So the number of samples that you need until you're happy can still be different between these two types of sampling approaches. So we need to know that number, and this is what we do here. We just call this generally the number n. And we see that depending on the system that we study, this is a kind of small system, only 16 visible spins, and 16 times 2, this alpha, 32 of these hidden units. And then we see, oh, actually, if we make it a little bit bigger, so to 22 by 22, actually, we see that the blue, which is here, this calculation with the icing machine, becomes lower and reaches the good value earlier. But if we go to a different system, actually, we see that the advantage is not so clear. So how can we now predict this? And there was something smart that Rutger Berns, the PhD student working on this, realized. Okay, this final accuracy, of course, is depending on the properties of this network. If we want to assess the sampling quality, okay, the most logical parameter to look at is the correlation time. So how long does it take before you get a sample from the distribution which is completely uncorrelated with the other, with a given sample. So that takes a number of steps, and that is what dictates this. And the beauty of this is that correlation time is a model property. It's just defined by this icing network that we have. So we can calculate this ratio of correlation times. We just calculate it for the moment on a digital computer. And then we get from that the ratio of this number of steps that we need. And with that, we can predict, if we know how many steps we need on one and on the other, we can find out where this advantage may emerge. So then we had to do, and actually this is a single graph, but this is really many, many digital computing hours. So sorry, we don't have these super good computers yet. And you see that depending on the network size, so for some reason this alpha S2 result is always kind of a factor 10 better than all the rest. But the important part is that the order of magnitude of this ratio of the number of steps that you need on one type of sampling and the other is essentially independent on the system size, what we named L here. So that means that we can make a very quick estimate, so we can just calculate. So now we do it for the most ideal case, but for all the others, it's just a factor 10 different. We see that, so here you see actually various types of calculations. This is now the time per sweep as function of the number of spins. So number of spins, horizontal axis, vertical axis is this compute time that you need until you're happy with your accuracy. And you see that this black line on top, that is the digital calculation. Actually, it's funny because it was done by a code that we termed ultra fast. Okay, in this graph you see it's actually not so ultra fast. The longer you do it, the more it takes. But okay, it was the best code that we had. And then we can make estimations, predictions, so we can kind of project what it would be if you would have this device. And we took a couple of literature references on, say, the designs that people have made so far. And then you see that already with kind of a conservative projection, how we call it, we gain a factor of 1,000 or a factor of 100 for the largest system sizes. So that makes us extremely excited. And if we do a simple calculation, so now we didn't do it as extensive as before, but we measured the energy on CPUs and then we compare that, we also see that we get a big factor improvement of the order of 10 power 5. So it's faster, it's more energy efficient, so that makes us very exciting. makes us very excited. Okay, so now I hope I convinced you a little bit about the potential of this hardware and the key idea that you change the effective computational complexity of your algorithm by just deploying it on different types of brain-inspired hardware. So what can we now expect more? Okay, I didn't tell you anything about learning. I taught you lots of things which were kind of in one way or the other depending on kind of training or trained AI models. But we didn't talk about the training yet, but also that, and this is a collaboration with a colleague in Nijmegen, Professor van Gerven, he devised a learning algorithm which is completely local. Like in the same way, the standard learning algorithms that we know are non-local. They require a rule that's called backpropagation. So that works very well. The training works perfect, but that's super costly. If you can do it locally, it's much better. And this algorithm predicts that you can do it not only local, but you can also just do it with noise. You can just inject noise, and then you get a proper estimate of how you should change the weights in order to have a better fit to your desired distribution. And then we tried that for some physical hardware together with the group in Mainz, which are very keen on making stochastic magnetic devices. And we showed, this is the first result on the simple benchmark, not yet on the computational problems that I want to apply it to, which basically show that, oh yeah, indeed, if you apply this rule, you get quite good performance, not as good as the baseline, like this, that you have for the backpropagation, but still very good performance. So that's very promising that we also maybe in the future can use stochasticity as a resource for training. And this is also an example of, so I'm kind of here alone as a representative of Radboud, but there's much more. I already mentioned the algorithmic research by Professor van Gerven, but we also have key expertise in materials, so this is actually very fundamental materials. Professor Kajatourians can make synapses as small and neurons as small as a single atom. So this we join forces together now in a neuromorphic computing initiative to bring this topic much further. And we don't only do that in Radboud University, but we do it across the whole Netherlands. Recently, we published a white paper on neuromorphic computing, trying to gather all the experts that we have. If you are interested in reading it, you can actually scan this QR code in which we try to explain in simple terms what is neuromorphic computing and why is it useful. And there are really many, many papers and many authors of this, many more that are not listed here. And one of the fantastic things of making a community together is that you can make a map like this. So we identify the key areas that you need for the development of neuromorphic computing. And what is also interesting to see here is that in the Netherlands, somehow we have a very good, say, ecosystem or a very good startup system. So because there are many startups, I once calculated there are order 20 or 25 startups in neuromorphic worldwide, and order 5 of them are in the Netherlands. So that's very interesting that we have that, and We also have them here, and we have many companies that in principle rely on a lot of computing and which would be interested also in finding out if neuromorphic computing is useful for them. So we also sketched the international landscape with real key experts, and I want to show one more. So this is also from Professor Ferber from Manchester. He was really behind Spinnaker, and now there's Spinnaker 2, and this lists as function of the year the number of artificial neurons that you can make in, say, spiking neural networks, which is really rapidly increasing. And this is another example that today we have, like this year, Intel Hela Point was launched. It's a neuromorphic supercomputer, a kind of hybrid. There are also lots of digital computing hardware connected to this. Also, the intrinsic spiking hardware is still based on CMOS, but we can now really simulate networks as large as the human brain. And this, from these cells, I also find it very exciting because this is commodity hardware, in principle, still what we call field programmable gate arrays. But already, if you do that and you reach the size, so this was the first supercomputer that can kind of simulate the size of the human brain with just 40 kilowatts. So that's already a lot less than this 50 megawatt that I was telling before. So that's why I'm so enthusiastic and why I think that in the near future we might be able to test this really large-scale hardware and really solve computational problems that we cannot solve today. So this brings me almost to the end. There are lots of people here, lots of collaborators, lots of acknowledgements. So the main research results were from 2 PhD students that I highlighted here. Many funding agencies, many people that contributed to the white paper. These are my summaries. I hope I convinced you about this fundamental computational advantage which is inherent in the new designs of these new types of hardware, which may have huge impact in science. And if we can discover how it works in science, I hope this also really accelerates applications in society and in industry. Thank you very much.